Okay, American derivatives. Who watched or read the slides for the European derivative stuff? Everyone. Good. Huh? No, that was the one 5 weeks ago. Right. Excellent, excellent. So does everyone know what an option is? What's an option? Someone tell me.
But not the obligation to buy and sell shares.
Yeah. It's the right, but not the obligation to buy or sell a share at a specified price. Okay? So usually in the European options, you can only exercise this option, you can only use this right to buy a share at the end, okay, at the expiration date. However, we're going to be exploring this other kind of a derivative called an American option, and this one allows you to exercise at any time up to the expiration. Okay, so European, you can only do at the expiration. American, you can do before as well. Okay, so introduction, as I said before, European option contracts specify an expiration date, and if the option is to be exercised at all, remember you don't have to, it's not an obligation, so you don't have to do it, but you have to do it on the expiration date for a European one if you want to. So an option whose owner can choose to exercise at any time up to and including the expiration date is called American. Okay, so these are the ones that instead of having to do it on the expiration date, you can do it any time up until the expiration date. Due to this early exercise feature, it's at least as valuable as its European counterpart. Okay, so in other words, it might be a little bit more that you have to pay this contract, right? Because remember, option contracts, you have to pay for them, right? People who weren't here for the other ones, let's give a little example of what exactly is going on. So say you have apples, right? And you don't know what the price they're going to be. But I give you a contract and you essentially say, look, I'll let you buy them from me at $2. Okay? Next Monday. $2 apples. Okay? And say I just give this to you for free. Right? And then say Monday comes next week and then apples cost $500. Okay? On the market. $500. Since you have this option, this contract that gives you the right but not the obligation to buy this apple from me, what are you going to do with it?
To buy apples at $2.
Yeah. So I have to give you an apple, $2, but then on the market they cost $500, right? So you buy it from me for $2, and you immediately sell it back to the market for $500, and then you make a lot of profit, okay? $498. However, if the apples, on the other hand, were 50 cents, what would you do next Monday if you wanted to buy an apple? Would you use up the contract and say, look, let's use it for, I'll buy it for $2, or would you just buy it at market price for 50 cents? Yeah, because it's cheaper, right? So options, they allow you to make a profit sometimes, or if it, other times they might expire worthless, okay? So in the, so basically these things, they're worth something, right? These contracts. And then we want to find a fair price for them, okay? So then we had an algorithm to do that from the European case. However, it's not exactly going to be the same with the American case. It might cost a little bit extra because you can have this extra feature where you can exercise early, okay? That's what that's saying there. The intrinsic value of the option is about the immediate payoff. So that's like there's the intrinsic value plus the premium associated with early exercise. And that's why we have like two sort of values here. We have an intrinsic value and then the extra value associated with that. And then in contrast to the case for a European option, whose discounted price process is a martingale, under the risk-neutral measure, discounted price process of an American is a super martingale. Basically what this means is, who knows what martingales are? We all commerce students? Yeah? Okay. All right, so like a martingale is basically when you have the expectation of something at n plus 1 given information up to n. So this thing is like fn is like information up to n. This thing is just going to be equal to xn. Okay, in other words, it's trying to say your best guess of, say I'm gambling at a casino, right? And I'm doing n games, right? So then I have information up to n. Okay. My best guess of what's going to happen next at n plus 1 is whatever happened before. Okay, that's what it's trying to say colloquially. Okay, super martingale is the thing that decreases, and then the martingale, sub martingale increases. So they're like these cases, right? Okay, so to price an American option, we're going to imagine selling the option in an exchange for some initial capital, then considering how to use this capital to hedge the short position in the option. In this case, we need to be ready to pay off the option at all times prior to the expiration date because we don't know when it's going to be exercised. We determine when, from our point of view, is the worst time for the owner to exercise the option. From the owner's point of view, this is the optimal time to exercise, and we're going to call it the optimal time. Okay. We then compute the initial capital we need in order to be hedged against exercise at the optimal time. Finally, we're going to show how to invest this capital so that we can hedge. Oh, spelling errors there. I think I've copy and pasted stuff from the book, so it's not detecting it properly. So we need to be hedged even if the owner exercises at a non-optimal time. We conclude that the initial price of the option is the capital required to be hedged against optimal exercise. Okay, so somewhat similar to the European case. So in section 4.2 of these slides, the basic American derivative security pricing algorithm when the payoff is not path dependent is going to be explained there. To try to develop a complete theory of this stuff, we're going to need stopping times, which we introduced in 4.3. After we have stopping times, we're going to do general theory of American derivatives, which is in 4.4. And then once that happens, we're going to look at a non-dividend paying stock, okay, in 4.5. So if people don't understand what's going on here, I would encourage you to go into the Discord and try to download the slides from previous weeks, which are somewhere in the Discord, because there's lots of theory that's being built up there. So I apologize if this is a bit too difficult. Yeah? Okay, sorry. Okay, so non-path dependent American derivatives. Okay, let's see what's going on here. Okay, so first we're going to review the European derivative. Okay, so is there do I have a, okay, there's a thing. Okay, so here's like the basic, let me skip to this first. Here's a stock, okay. Stock is worth $4 initially. Then either, in this model, we flip a coin, okay, like hypothetically. If the coin lands heads, stock goes up. Stock lands, the coin lands tail, stock goes down, okay? And we also assume that the up factor is 2 and then the down factor is a half. Okay, so the 4 is either going to double or it goes down. And then again, on the next flip, we flip again. If it's tails, it goes down again. If it's heads, it'll go up, and so on and so forth. Okay, is this clear what's going on here? There's a stock and it's going up and down. Yeah? Okay, so then what do we do with an option? Like, you know, if I have the right to buy, but not the obligation to buy at some given time, how do we price this? Usually we price it like this, okay? Yeah, okay, that's the European one, and then that one's the American. Okay, so here's what we do in the European algorithm. We have this Vn of S equal to this formula here, okay? So what is this formula? This basically says, so we have an interest rate R, okay? what we try and do here is we trade a combination of stocks and bonds to try to replicate the price of the option. Okay? So R is the interest rate in the bond market. And then P tilde and Q tilde are called the risk neutral probabilities. Okay? They're basically they're like probabilities. They're not the actual probabilities of the stock going up and down, but we can treat them as some kind of probability, okay? So we basically have this recursive formula, P tilde Vn plus 1, of the up factor, okay? So that's the amount, the factor that the stock goes up, multiplied by the price, plus Q tilde Vn plus 1 ds. Okay, so basically we work backwards when we do this. So if we're given Vn plus 1 and the up and down factors, what we do is we substitute those in to get the price of Vn. This is Vns. So we substitute in S, which is a stock price. Then we get back the price beforehand. Okay, so I'm not sure if there's a. Do we have a? Okay, so here's like the prices for. Okay, this is an American quants. But basically, what we're trying to do is once we have these two values, okay, we plug them into a formula. So this is an American one. This is the European algorithm. However, we essentially plug the up value, that's what it's saying here, up, and the down value. We plug them into this big formula here, and then we get out a price, this one here, okay? And then we do it again with these two, and then we get another price here. And after we have these two prices, we can calculate this, okay? So if you ever want to calculate something like this, what you do is you do this recursive formula, okay? You put the tree down, and then you can sit there and figure them out, okay? So yeah, we also have Vn, capital N of S, being equal to the maximum of GS and 0. Okay, the reason that we have the maximum of GS and 0 is because options can expire worthless. Okay, that's in the case when the option is the stock is below. Is below the strike price. Okay, so for example, in the case of apples, if the apples are 50 cents and you have the option to buy them from me for $2, this option is worth nothing. Okay, you don't want to use it. Does that make sense? Yeah. So it can be worth 0, but in the case that it is worth something, if they're $500 apples, then it's worth $498. Okay. So that's why we take the maximum there. So that's the European one, and then the replicating portfolio, which is the way we set it up in the what do you call it, stock and bond market, is going to be that thing there. Okay, but then onto the American one. Payoff function G is going to be specified, so that's just whatever, how much it pays off when the stock price is S. Then at any period n less than or equal to capital N, the holder of the derivative security can exercise and then receive payment equal to G of Sn. So in this section, the payoff is going to depend only on the current stock price Sn, not on the path. Okay, so sometimes we can have things that are dependent on the path, but so like this, right? So in this case, you know, if you get to here, that's all you need to know, right? Because it doesn't depend on the stock path, just the price. In the other section, we're going to do like what happens if it depends on the path. Like if it went up and down, that's different to going down and up. Okay, so just keep that in mind. Then, so here's the formula for the American option. We have to take the maximum instead. Okay, so There's still that formula in there. Okay, so this thing here. But then we have to take the maximum with GS. Okay, horrible writing, but that's what we do. And the reason that we take the maximum is because we can exercise earlier, right? So it's going to depend on previous guesses of GS, okay? Not just this formula. Does that make sense?
GS.
So basically, GS is like the payoff at time S. It's you exercise, GS is equal to you exercise the option given a certain stock price, the amount you receive. Yeah. And then, so the difference between these two formulas is that in the European case, it's just the 1 over 1 plus R thing. But in the American case, we have to take the maximum of that thing and GS. Okay? So when we do the recursion, we have maximums and stuff, so it takes a little bit longer. Okay, here's the thing that it's not exactly on the board because I didn't put the prices, but imagine we have this thing here. Okay, so we have an American put option. So the put option is the one where it allows you to sell at a particular time, okay, not buy. Let the interest rate be a quarter, let the risk neutral probabilities be half. Consider an American put option expiring at time 2 with strike price 5. Okay. So this basically means that, let me rub this off. This basically means that we have GS equals 5 minus S. For call options, we usually have the K, we have like this, the price minus K. So like in the case of apples, right? If I have to buy an apple, the fair price of the option is going to be like, you know, if you can buy the option from me at $2, sorry, the apple, then it's like you take away $2, right? And then you have the price of the apple here. So if the price of the apple is 500, then that's going to be what, 498, which is what we said earlier. Yeah. However, if they cost 50 cents, well, you know, it's going to be negative, right? Which doesn't really make sense because we don't want to lose money here. So that's why we take the maximum of stock price minus K, 0. Yeah? That's the formula for the call option. Yeah? Agree? And then what's the formula for the put? Be the opposite. So that's why we have the K minus S here. Strike price is 5, so K is the strike price minus S. So V2 is going to be equal to the maximum of 5 minus S, 0. And then Vn of S is equal to that big thing there. Okay, so that's the maximum of 5 minus S over 1 over 1 plus R. So 1 over 1 plus R is just 2 over 5 there. And then with Vn plus 1, 2S, Vn plus 1, S on 2. Okay, so let's see if we can compute this. Let me draw up these things on the board. So this one here is $16. This one over here is $4. And this one here is $1. Okay. can we calculate what V216 is, V24 is, and V21 is? Okay, so V216 is basically saying if I exercised my option when the price is equal to $16, the stock price is $16, how much money am I going to get? No, sorry, not how much money. What's the option worth? Okay. So using these formulas, what can we try to do? This is V2, by the way. V2, we have a formula for V2. Okay. Anyone know? This is the easier one because it's just V2 is this, yeah? V2 of S. Yeah. Maximum of 5 minus 16. Yeah, so for 16, what happens? Yeah, for 16 it's 0. Why is it 0? Because the maximum of 5 minus 16 and 0 is 0. Yeah?
So is the price? So it's 5 from the previous article.
Sorry?
Is it 5 for 16 for
The strike price, yeah. Strike, that's just a strike. It's just like, I can sell the option at $5 if I want to. Okay. So then we do the same thing again, okay? V2 is time for 4. What do we do now? Yeah? 1? And then what about for 1? Yeah? Okay, good. Yeah, okay. So, yeah, 0, 1, and 4. Okay, good job. So next, how do we calculate the prices in 3.31? This one again. How are we going to calculate V18 and V12? Start with V18. So using this formula now, how do we calculate V1 of 8? You don't know? Do you want to have a crack on the board?
Wait, V18?
Yeah. So using Vn of S, how can you do that?
Wait, we check V216 and
Yeah.
find
Yeah.
V216?
Yeah, we've already found this.
Oh, okay.
Yeah.
V216, V24.
Yeah. So you plug those in.
Maximum 5 minus S, how about 205 times V216, correct?
Yeah.
And V24 is 1. So it's maximum 5 minus S, comma.
And 8 is S this time. So 5 minus 8
I
on
guess max value is 1.5.
us. So 0 and 1. Yep. So this is 1. Yeah. And then how about the other one? Who wants to do that? 2. Yeah, V1, 2.
4 and 4. V24 is worth 1. 1 is worth 5 is worth 5. So right hand side.
What is it? 1 plus 4, yeah. Yeah, should be. Oh wait, what happened here? Yeah, 2 and 5. No, that one's 3. Yep. Okay, so now V04. What do we do there?
When you go from like fractions or decimals.
Yeah, it's fine. Yeah. And then how do you do V04? Just plug it in again. Yeah? So then that's going to be 1.36. Okay? So that's the fair price of the option. Okay? So if you want to calculate, I get to sell you at $5 for, I get to sell the stock at $5. The fair price of the option at time 0 is going to be $1.36. Okay? For the American option, which includes early exercise. Okay? So there are the prices there. So this algorithm gives different results compared to the European algorithm, because V1 or V1 of 2, where the discounted expectation of the time 2 option price is going to be 1 over 1 plus R with 1 plus 4, which is basically, where was it? That one there. Okay, V1 2. Because V1 of 2 is strictly greater than the price of a comparable European put, the initial price V0 of 4 for the American put is also strictly greater than the initial price of a comparable European put. Okay. Let us now reconstruct the replicating portfolio. We begin with initial capital $1.36 and compute delta 0. Okay, so that the value of the hedging portfolio at time 1 agrees with the value of this option. The first toss results in a head, and this requires that 0.4 is equal to, oh wait, I forgot to put page numbers on this. Anyway, yeah, I don't have page numbers, so yeah, doesn't matter. So if the first toss results in a head, then this requires that 0.4 is equal to V1 of S1 of H, which is going to be equal to this thing because that's the way we replicate it. So this is basically, if you don't know what this is, it's like we've borrowed, so we've got an X0, right? That's our initial wealth, and then we have to borrow money from the market. And then we borrowed this much, okay, which is the amount of stocks we own. Delta 0 is the amount of stocks we're getting. And then S0 is the stock price, okay? So that got taken away from our initial wealth. And then ultimately we have to borrow this much, yeah? Then at the next time, what ends up happening is that we've bought this stock with this money, and then this stock is now worth this much in total, okay? Because it's gone up in this case, and then we have that amount of stock multiplied by the value of the stock, and now we have to pay back the bond market 1 plus R. Yeah. Yep. And then plugging in the values, we just get 3 delta 0 plus 1.7, which implies that delta 0 is equal to negative 0.43. Okay, so if delta is negative, we're giving away stocks. We're shorting stocks. Okay, we allow for short stocks in this model. On the other hand, if the first coin toss results in a tail, we similarly have this thing, which again gets us delta 0 equal to negative 0.43. And then we could have found this by using the value, finding the value of delta 0 by substituting it into this formula here. Okay, so this is the way to find the replicating portfolio amount of stocks you need. Yeah, and then we would have this thing here, which is again negative 0.43. In any case, we begin with the initial capital $1.36 and take a position delta 0 shares of stock at time 0. Then at time 1, we will have x1 equals v1, regardless of the outcome of the coin toss. Let us assume that the first coin toss results in a tail. It may be that the owner of the option exercises at time 1, in which case we deliver to them $3 value of our hedging portfolio and no further hedging is necessary. However, the owner may decline to exercise, in which case the option is still alive and we must continue hedging. We consider in more detail the case where the owner does not exercise at time 1, after a first toss resulting in tail. We note that next period the option will be worth $1 if the second coin toss results in a head, and $4 if the second coin toss results in a tail. The risk-neutral pricing formula says that to construct a hedge against these two possibilities at time 1, we need to have a hedging portfolio valued at, this is just 1 over 1 plus R, and then these are the, P and Q are taken outside as well, and then those are the formulas to get the recursion thing going. And then so we can consume $1 and continue to hedge with the remaining $2 in our portfolio. As this suggests, the option holder has let an optimal exercise time go by. More specifically, we consume $1 and change our position to a delta 1 T shares of stock. Okay, so when you're replicating the portfolio, you can at different times have a different amount of stocks. All right, so if you're holding 5 stocks at first, you can hold 4 stocks next time to try to hedge. Okay, this stuff might not be entirely clear, but have a look at the European slides to have a look at what's going on here. Basically, we're getting a combination of stocks and bonds, and then we're just forcing it to equal to the thing. Yeah. The $1. So it's like we're trying to force it to be equal. So the way it's like, so it's like we have $3 here for the payout. So then you can like use up $1 here for the stock, and then you have $2 remaining. Does that make sense? It's like, it's difficult to explain, but it's basically like you have a combination of things, right? And then you have like, so for example, if I short $1, yeah, I get $1, you borrow my $1 stock, and then I can like invest that $1 into like the bond market or something, and then I get like a combination of these things going. Does that help at all? Or not really.
Oh, so where's like the $1 go? That you've got more money than the portfolio. You got $3, and the portfolio was valued at $2. Is that right?
Yeah.
So you can, as you just say, like you keep the extra dollars of profit, and you keep going. So it's like some of the ideas with all of like buying, it's just like hedging. There's like you don't want to bet on something and like not have like a backup plan. But it's like with an option, you're kind of betting that price. Let's just say if you're doing calls, the price is going down.
Yeah.
Right. So since you're making bets, the price is going down. You want to have an alternative position where if the prices don't go down, you will still benefit. That's what hedging is. You're betting on the opposite of what's actually going to happen. The idea is that like if either of those are sliding this price, you have to make like a little bit of money for a lot longer. In this case, using the $1 to hedge your position. So to like bet on the opposite outcome of what you think is going to happen. So just minimizing losses and minimizing. Yeah.
Does that make sense?
Yeah.
Yeah.
Using the $1 to arbitrage things. Yeah. It was targeted to.
Oh yeah. The other thing to mention is that this is like it's an arbitrage-free price. So what that means is like, how do I explain this? I'd need to go back to the other slides, I think. But basically, if the price of the option at V0 is not fair, you can make free money. Okay, that's what it's basically saying. And the way they prove that is like they do again a combination of buying and selling these things, and they hedge certain things, and then all of a sudden you make money, right? I'd need to go back to the slides, but for the previous few weeks, but Yeah, and this is saying more stuff about if the second toss is a heads, then we want this thing to be true. So this implies that delta 1 t is equal to -1. Similarly, if the second toss is tail, then we want 4 equals this thing here, which is going to be equal to -1 again. Okay. We can also get it with this formula here, the v2 of 4 minus v2 of 1 divided by 4 minus 1. For sake of completeness, we will finally consider the case where we have the first toss resulting in a heads. At time 1, we will have a portfolio valued at x1 of h. We choose delta 1 of h equal to, we sub it into the formula, we get -1/12. And if the second toss is a heads, then at time 2, the value of our hedging portfolio is going to be this thing, okay, which is equal to 0. If the second toss results in tail, at time 2, the value of our hedging portfolio is this thing here. So maybe, like I'm not introducing it here, because it's sort of assumed knowledge, and I'm sorry about that, but what we're basically doing is we have this combination of stocks and bonds, right? You see that? This is a combination of stocks and bonds. This thing here, this 5/4, is the 1/1 plus R. Sorry, it's the 1 plus R thing, yeah? So our interest rate was a quarter, yeah? 1 plus a quarter is 5/4, yeah? So that's basically saying we've borrowed some amount of money and then we have to pay it back, yeah? And then this thing is like, the thing is worth $16 now, and we have this amount of stock, yeah? And what we've done is we've forced it to become the option price, which is 0, yeah? Remember we got 0 for B216? Yeah, so basically all the way down, we have like this replicating portfolio, forcing it to equal the option prices. And because we can do that for time 2, then we can trace our steps back to time 1, then we trace our steps back to time 0, where we get the fair option price. Okay, so that's what's going on. Finally, we'll consider discounted put prices in the following diagram. Okay, so these are discounted prices. This is basically like, you know how like money has a time discount? Like if you have $40 and you just leave it there, like you could have invested it, right? Like current times 1 plus R equals future. Yeah, like you're getting money from it, and then you can swap them around and say like current equals future. So this thing is called like the discount, because it's like, oh, you know, my money's just sitting there in my bank account, and it could have made 1 plus R, right? So we sort of say like, oh, you know, my current money is my future money discounted. Then we divide it by 1 plus R. So that's what we're doing here, right? We're dividing by 1 plus R for these on these option prices, so they become discounted. So does that make sense?
Yeah. Anyone not understand what you just said? It's like pretty important. You don't understand this. Is it supposed to be 1/1 plus R to the hand? Why is the rate going to change?
Yeah. Sorry.
Like interest will change. Yeah, I understand, but you see over here it's
Yeah. Sorry. That's like the n equals 1 case, but yeah. N should go to the power of something. Yeah. Sorry, the 1 plus R should go to the power of n. Yeah. So these constitute a super martingale. Basically, if you took the expectation of this, then it's going to be less than x. So it's a decreasing process. Each node, the discounted American put price is greater than or equal to the average of the discounted prices. So in this case, like we had these two things equal this. In the other case, we had those two things equal this. In this case, these two things subbed into the formula is like bigger than that. Oh, sorry, less than that, is it? Say. Yeah, it's greater than or equal to the average. So so these ones are less than that. Okay, which means that like the expectation is going to be less than or equal to this. Yeah, so it's a super martingale. The following theorem formalizes what we've seen. Consider an n-period binomial model with this condition here. Basically, this condition is basically saying the down factor of the stock. So like when the stock goes down, it's going to be is less than 1 plus r, which is less than u. Okay, and that's an important condition to have. In fact, if you remove that condition, you get arbitrage. Okay, which is we don't want arbitrage in our model because you can make money out of nothing, which doesn't make sense. Now, in practice, you will see arbitrage pop up, but it's like someone finds it and they buy and sell and they make money, so it goes away. But basically, we're going to have the recursively backwards function. We also have the delta n, so the amount of stocks in our replicating portfolio time n, and the value cn, which is this thing here. Okay, bn minus 1 over 1 plus r, which is the expectation. Okay. If we set x0 equals v0 s0 and define recursively forward in time the portfolio values x1, x2 up to xn by that value there, then we will have xn of all the omegas equal to vn of all the omegas for each of the omegas. In particular, xn is going to be greater than or equal to g of s. Okay. The wealth equation introduced in this theorem is the same as the wealth equation in the European option. So that's the wealth equation there, because this is basically saying, so this xn is our portfolio, okay? The xn plus 1. So basically it's like we started with this initial wealth, and then we're doing some stuff in the stock and bonds market, and then we're replicating it, okay? So again, this is like the stock price at n plus 1 and the amount of stock you got at time n. And then you have the 1 plus r paying back whatever stuff you had there. Which in this case is the xn minus cn minus the amount of stuff you got. So the wealth equation is the same there. This theorem guarantees that we can hedge a short position in the American derivative security with intrinsic value G of Sn at each time n. In fact, we can do so and perhaps still consume at certain times. So the value of our hedging portfolio Xn is always at least as great as the intrinsic value of the derivative security, because these two things are equal, and because of the fact that Vn is equal to GS. This big formula here, and this thing guarantees that Vn is always going to be greater than the payoff. The non-negativity of Cn also follows from 4.2.6, which, what's 4.2.6? This thing here. Which implies that Vn of Sn is greater than or equal to the expectation of the Vn. Okay? So it's a super martingale, again, right? Because it's going to be bigger than or equal to the expectation. In other words, the expectation of it is going lower. Does that make sense? So it's like I had a turn at the casino, say, xn. So let me do it up here. So you see this thing here, they're equal. It's like if I had a turn at the casino, I want to see what my next turn is, given information up to n. And then it's like, it's going lower than the thing before, right? Does that make sense? So, how do I explain it? It's like, this is my information. This is like my next turn at the casino. I roll a dice, I play a game, whatever, or do some stocks. And then it's going to be like what I'm expecting to happen in the future is worse than what happened before. Yeah, because it's less. Does that make sense? Yeah? Okay. Stopping times. All right. Section 3. So the idea of a stopping time is like, I'm gambling at a casino, and then at any given time I can stop. Okay? Perhaps like there's two ways I could stop at a casino. Either like I win a certain amount, like I start with $5 or something, and then I get up to $20 and then I want to stop, or I go broke and they kick me out. Okay? So this is where the example of stopping times comes in. We have these times where you can stop. Okay? So in other words, the reason this gets introduced into American options is because you can at any time you want stop and exercise. Yeah? As opposed to the European one, where you can't exercise. So it's going to depend on the price movements. Okay? We claimed in the example above that if the first coin toss results in tails, then the owner of the American put in that example should exercise at time 1. On the other hand, if the first toss results in head, then the owner of the put should not exercise at time 1, but rather wait for the outcome of the second toss. The first toss results in a head, then the stock price is S1 of H equals 8, and the put is out of the money, okay, because 5 minus 8 is just going to be 0. Okay, I don't want to sell, if I can have a stock, I don't want to sell it at $5, I'd rather sell it at 8. Okay, so the option is just sort of sitting there. 16 is also out of the money. The owner should let it expire. On the other hand, if the stock price goes to 4, then it's in the money. Okay, then we should exercise at that time. Okay, so because we'll get $1. So describing this exercise rule, we'll have stopping time of HH equal to infinity, the stopping time of HT, so stopping time of HT equal to 2, stopping time of TH equal to 1, and the stopping time of TT equal to 1. Okay? So the reason it depends on the path is because, like, in this one, like, we know the future, right? But in practice, we're not omniscient, right? We don't know what's going to happen in the future. We don't know if it's going to go up or down. So we basically have to do what we can, okay? So here's like the rule, right? We have, like, if it goes, so we shouldn't exercise here. If it gets to this point here, then we exercise. If it goes up, we don't exercise. If it goes down again, we'll exercise. Or if it goes up, we just won't exercise at all. Okay? On those paths where tau takes the value infinity, we mean that the option should be allowed to expire without exercise. It's just a definition. In the example from the previous section, there is only one such path corresponding to HH. In the event the coin tosses result in HT, exercise should be done at time 2. In the event the coin tosses result in TH or TT, the exercise should be done at time 1. Random variable defined on omega equals listing, which is basically, what is that? Just the sample space. By the exercise rules in the set 0, 1, 2, and infinity, we can think of it as stopping the American put hedging problem by exercising the put at least on 3 of the 4 sample points in omega. It's a special case of a stopping time as defined below. So here's an exercise rule. We have, so we exercise them at these different price points, and then we get 0, 1, and 2. The owner of the put of this example will regret not exercising the put at time 0 if the first coin toss results in a head. In particular, if they had foreknowledge of the coin tossing, she would rather use the exercise rule 0, 0, 1, and 2. Okay, if we could use this exercise rule, then regardless of the coin tossing, we would exercise the put in the money. The problem with this exercise rule, row, is that it cannot be implemented without insider information. Okay, so again, we're not omniscient, right? And we have to account for that. Cause for the decision of whether or not to exercise at time 0 to be based on the outcome of the first coin toss. The first coin toss results in a tail, then the decision of whether or not to exercise at time 1 is based on the outcome of the second coin toss, and so it is not a stopping time in the sense of the definition below. And here's what the definition is. Yep. In an n-period binomial model, stopping time is a random variable tau that takes values 0, 1 up to n, or infinity, and satisfies the condition that if tau of this thing equals n, then tau of this other, so these coin tosses are like n other coin tosses, okay? So if they're all equal to n, for all of these values, it's a stopping time, okay? So the condition in the definition above is that if tau of that thing there, then tau of the new thing with the n plus 1 up to n changed for all of these new ones ensures that stopping time is based only on available information. Okay, because we're at time n and we're not omniscient. Yeah, so we want to ignore those somehow. Yeah. Whenever we have a stochastic process and a stopping time, we can define a stopped process. For example, let yn be the process of a discounted American put price in the figure from the previous section. So it's this thing here. Then let tau be the stopping time from the figure. Okay, this one here, stopped process. See, I've referenced pages and I don't have page numbers. It's unfortunate. But we're going to find a stopped process y n max n minimum t. This thing is a minimum. Okay, so what this is basically saying is like it's either going to stop at time n or time tau. Yeah, we're going to stop it early. Or we're going to let it go. Similarly, for the 0 tau is like we're either going to let it go to 0 or like stop it at tau. Yeah. So y is 0 and tau. So the minimum of 0 and tau is of course going to be 0. The minimum of 1 and tau is going to be 1, because tau is going to be bigger than that. So, however, the minimum of 2 and tau depends on the coin tossing. If we get HH or HT, then the minimum will be 2. If we get TH or TT, then we're going to get the minimum 1. Okay? So we're going to have 4 cases. Okay, these 4 cases. Won't read out those numbers, but there they are. Note in this construction that the process continues on past time 1. Even if tau takes the value 1, time is not stopped. However, the value of the process is frozen at time tau. A better terminology might be to call this a frozen process. Okay, but this term stopped process is already in universal use. So basically, it's like time doesn't stop there. It's like the thing keeps going. It's just we've sort of exercised it or whatever. Okay. So there's the stopped process. The discounted American put price, that one there. That's like 1 over 1 plus r to the n, the discounted thing up there. In figure 36. Okay, so that's like up there somewhere. It's a super martingale, but not a martingale under the risk neutral probabilities. Essentially because of this. Okay. So it's bigger than the expectation. Martingale, is that correct? Yeah, because it's the expected value is getting lower and lower, so it decreases. Okay. Stopped process is then a martingale, and in particular, it's equal to this, okay, 2.4, which is half of the expectation of those things there. The observation is true generally under the risk neutral probabilities. A discounted American derivative security price process is a super martingale. However, if this process is stopped at the optimal exercise time, it becomes a martingale. The owner of the security permits a time to pass in which the super martingale inequality is strict. They have failed to exercise optimally. We have just seen an example that we can stop a process that is not a martingale and thereby obtain a martingale. Of course, if we stop a process that is already a martingale, we will obtain a process that may be different but is still a martingale. The trivial observation is one consequence of a general theorem about stopping times called the optional sampling theorem, which we'll talk about now. So here's the optional sampling theorem. Here are these super martingale, martingale, and sub-martingale things again. So basically, a martingale stopped at a stopping time is a martingale. A super martingale stopped at a stopping time is a super martingale, and a sub-martingale stopped at a stopping time is a super martingale, sub-martingale. Okay, so we also have these three things are true. So the expectation of x of n minimum t. So that's like the smaller one that we stop at, yeah, because we either stop at n, like when we're finished, or we stop early. Yeah, it's going to be less than or equal to the expectation of x of n. Similarly, for the super martingale, the expectation of the stop time is greater than or equal to the expectation of xn. And for the martingale, the expectation is going to be equal. Okay. We illustrate the first statement of the theorem with an example. Figure 4.3.4 below, this one here. So discounted stock price. So it's the stock price we had earlier, but discounted. So we have 1 over 1 plus r to the n of Sn times Sn. This is a martingale under the risk neutral probabilities path. At every node, the value of the average value is the average of the values of the two subsequent nodes. Okay. In the figure even below that, we show the same process stopped by the stopping time tau. In slide 47, again, at every node, the value of the average of the values at the two subsequent node. Okay, so there's discounted stock price. There's discounted stock stopping time. So we've stopped it there earlier. Some things different. Yeah. It is again priced. It's dependent this time, right? So these two aren't the same. And then here's so when it stopped at a non-stopping time. So for rho, that thing we had earlier. Figure 4.3.3 shows a super martingale stopped at a stopping time and the resulting process, which is of course still a super martingale. This illustrates a second statement in the optional sampling theorem. Finally, we note that if we stop the discounted stock price process of figure 4.3.4 using the random time rho of figure 4.3.2 on slide 49, which is not a stopping time, we destroy the martingale property. Figure 4.3.6 shows the stopped process. The random time rho looks ahead and decides to stop if the stock price is about to go up. And then this introduces a downward bias in the discounted stock price. Sub-martingale has a tendency to go up. In particular, if xn is a sub-martingale, then the expectation of xm is going to be less than or equal to the expectation of xn whenever m is less than or equal to n. This inequality still holds if we replace m by stopping time minimum tau and n, where tau is a stopping time. The expectation in the optional sampling theorem is computed under the probabilities that make xn be a sub-martingale or super-martingale or martingale. In particular, if xn is a sub-martingale under the risk-neutral probabilities in a binomial model, then the conclusion of the theorem would be that the risk-neutral expectation of x stopped at either n or tau is less than or equal to the risk-neutral expectation of xn. Okay. Want a small break, and we'll move on. Okay, general American derivatives. All right. So, in this section, we introduce American derivative securities whose intrinsic value is permitted to be path dependent. Okay, so can depend on the path. We define the price process for such a security and develop its properties. We also show how to hedge a short position in such a derivative security and study optimal exercise time. So we'll be working with the n period binomial model, capital N, up factor U, down factor D, interest rate R. Again, no arbitrage condition is there. In such a model, yeah. There's a proof of that in the European slides. So, are you on the Discord?
Yeah.
You can try to find it there, or maybe contact him to try to get it. Like it's just called like it's just called binomial.
Those options pricing.
Yeah, that one.
Yeah, it's not what it's actually about, but like options pricing workshop sounded like the best.
It is. It is option pricing.
It's in the learning channel. In the workshop.
Yeah.
No. Learning workshops.
Yeah. They're option pricing workshop. Yeah. Yeah, this one here. There's a bit of a proof somewhere. Yeah. Yeah, there. Oh, no, it's yeah, this one there. They go up. Oh. Yeah, I'll go up a bit more. A little bit more, maybe. Yeah, here. We now prove that there's no arbitrage. Yep. So there's the proof there. You can have a look at that. Yeah. It's basically like you can start shorting things and doing things, and then you
have to assume that arbitrage doesn't satisfy.
To get our fair value, yes.
So you're always working with an interest rate.
Yeah, because we're buying and selling the bonds.
And it's never like never just doing your own.
Well, here's the thing, right? It's not like it's difficult to explain, but it's like we're not actually buying and selling bonds. Okay, this is a model where we're saying like if we were buying and selling bonds, we can in these cases up here, because like this thing is a big mystery. We don't know what it is. Yeah, these things we can kind of know. So if we force those things to become like a replication of stocks and bonds, like we're not literally sitting there doing replication in the market, but we're just using it to find the price. And once the price is like, okay, look, this is the fair price. Yeah. So.
Okay. Because when I don't know, maybe I got wrong, like an easy example. Like we're trying to always find the S0 price.
V0 of S. Like S0 is already given, but it's like, okay, if I was at time 0 and I have an option.
But how we like with that knowledge.
Yep.
Isn't it past time 0 then? So like how we'll know later if it was a good price.
Like there's a unique price for fairness. Right? So it's unique. So it's like once you get, how do I explain it?
I understand how we get back to it.
Yeah.
What if the time already passed?
Yeah. Like we're not literally saying that. Like it's not like we have to go into the future to do these things. We have a model. Right. Like we're just saying like, okay, if the stock goes up to this, if the stock goes down to that, then
we're making a guess.
Yeah, we're making a guess. We're not. Yeah. So for this kind of thing, it's like these things haven't happened yet, right? We're just doing this on paper. This is not like really in the market. Yeah, this stuff hasn't happened, but it's like assuming it did happen. Assuming like we don't know what the up factor is going to be. You know, of course, it's not like every minute it just doubles or halves. Yeah, this is a model, but it's like if it were doing that, then we can try to trace it back. Yeah, and you don't have to wait for it to actually happen. You just like pretend it happened. Yeah. So then, if we were ever in a situation where the initial price is 4 and we had a stock strike price this and that, then our fair price would be whatever we calculate. Yeah. Does that make sense? Yeah. Okay. Yep. So then, in this model, we have a set Sn. It's a set of all the stopping times that take values in this set. In particular, what's this? S0 contains every stopping time. I'll fix that. Stopping time in Sn can also take the value n on some paths and the value infinity on others, and can't take any other value. So the definition. Okay, this thing here is an indicator function. Does anyone know what an indicator function is? Okay, so it's like it's just like it equals 1 when it's on that set, and it equals 0 if it's not on that set. Okay, so it's like if I say this thing here, it's like say I equals 0, 1, 2, then say I roll a dice, and it's like if I rolled a 1 or a 2, then this thing equals 1. But if I rolled like 3, 4, 5, or 6, which is not in here, then it becomes 0. So in this case, it's like, okay, if the tau, our stopping time is like less than the n, then it's going to be 1. But if our tau is ever more than n, then we make it 0. Okay. So we define the price process Vn equal to this thing. So we have Gn is a random variable depending on the first n coin tosses. The American derivative security with intrinsic value process Gn is a contract that can be exercised any time prior to and including n, and then it will pay off Gn. Okay. So we define this price process Vn. It's going to be the maximum of the stopping times of the risk neutral expectation of basically 1 over 1 plus r about tau minus n g tau, and multiplied by the indicator function. The idea behind this definition is that if we suppose the American derivative security is not exercised at times 0 up to n minus 1, we're trying to determine its value at time n. At time n, the owner of the derivative can choose to exercise it immediately or postpone exercise to some later date. The date at which they exercise, if they do exercise, can depend on the path of the stock price up to the exercise time but not beyond it. In other words, the exercise date will be a stopping time tau. Since exercise was not done before time n, this stopping time must be in Sn. Of course, if they never exercise, tau is equal to infinity, and they receive 0 payoff. The indicator function appears to tell us that this thing should be replaced by 0 on those paths for which tau is equal to infinity. When the owner exercises according to a stopping time in Sn, the value of the derivative to them at time n is the risk neutral discounted expectation of its payoff. They shall choose tau to make this as large as possible. Okay. One of the immediate consequences of this definition is that Vn is equal to max Gn 0, okay, which is that thing we had up here. To say this, if we take n is equal to big N from the definition, it's going to become the supremum of tau in n of this thing here. Okay, so it's the greatest upper bound. Wait, is that the lowest one? Victor. Which one's supremum, which one's infimum?
The what, sorry?
Supremum. It's the greatest. Lowest upper bound? No?
What?
Is the lowest upper bound or not?
What?
The lowest upper bound.
Lowest upper bound of
Wait. The least upper bound. Yes, the least upper bound.
Okay.
So I always get them mixed up. Right. Or 4. Yeah, we have 30 minutes left.
Arguably 4.
Yeah. So a stopping time in Sn takes the values n and infinity, and for such a stopping time, this is true. Okay, so we can get rid of that thing there. In order to make this as large as possible, we choose tau equal to n, and if Gn is greater than 0, and tau is equal to infinity if Gn is less than or equal to 0. This choice of tau, we have the when tau is equal to n, Gn will be equal to the maximum of Gn and 0, and we claim that Vn is equal to the maximum of Gn and 0. So here's the intrinsic value of G. We continue with the example on slide 18. In the second section, the American put with strike 5. The stock given in the figure of slide 17, the intrinsic value is given in figure 4.4.1 on slide 78 just above. In this example, n equals 2 and Vn is equal to the maximum. And these are the values of Vn because we take Gn and 0. So there's Gn and we take the maximums. Okay. This thing here. So it's like we take the maximum. So it's going to be 1 and 4. Yeah. It's the intrinsic value of the American option. Yeah, the intrinsic value. So it's like there's this extra premium you have to pay for being able to exercise early. Yeah.
What's the value of how much it costs?
It's the value of how much it costs minus how much extra you paid. Yeah. So that's what they are there. Then we apply this big formula here, big scary formula. We get subbing in n equals 2, we get tau is less than or equal to 2 with tau minus 1 times g tau, given the information at time 1 of heads, which is a big function. To make the conditional expectation on the right-hand side as large as possible, we take tau of getting 2 heads equal to infinity. So we don't exercise in that case, and we take tau of heads tails equal to 2. So we exercise at time 1, it goes heads tails. The decision of whether or not to exercise at time 2 is based on the information available at time 2. So this does not violate the property requiring stopping times. The exercise policy makes the right-hand side equal to essentially 0.4. We now have the same thing in case of tails. So we get this thing here. To make the conditional as large as possible, we will either exercise at time 1 or time 2. It's clear that we want to exercise at one of these 2 times because the option is in the money, regardless of whether what the second coin toss is. So if we take both of them equal to 1, we'll get the value of 3 out of the equation. We get the value of 2, then we'll get 2. We cannot choose tau of th equals 1 and tau of tt equals 2 because that would violate the property of stopping times. We see then that v1 of t is the maximum of the expected value of the risk-neutral expected value of the 1 over 1 plus r to the power of tau minus 1 times g tau. And this would yield v1 of t equals 3. Finally, when n equals 0, we have this maximum equation here. So that's not given anything. There are many stopping times to consider, but a moment's reflection shows that one can make this as large as possible if these taus hold. Okay, so infinity, 2, and 1. This stopping time, it'll become 1.36, which is what we got earlier. Okay. Yeah, so that's what we got earlier. There's the American put prices there, which was also from before. So here are some properties of the American derivative. Vn is greater than or equal to the maximum of Gn or 0. So that's just seen as a premium. The discount of the process is a super martingale. If Yn is another process satisfying Yn greater than or equal to the maximum for n, and that one's a super martingale, then Yn is greater than or equal to Vn for n. So we can say that Vn is the smallest process satisfying 1 and 2. Okay. Property 2 in the theorem guarantees that an agent beginning with initial capital V0 can construct a hedging portfolio whose value at time n is Vn. Property 1 guarantees that if an agent does this, they have hedged a short position in derivative security. No matter when it is exercised, the agent's hedging portfolio value is sufficient to pay off the derivative security. Thus, 1 and 2 guarantee that the derivative security price is acceptable to the seller. Condition 3 says that the price is no higher than necessary in order to be acceptable to the seller. This condition ensures that the price is fair to the buyer. We have the following American pricing algorithm for the path-dependent derivative security price process given in the definition. We have V capital N is equal to the maximum of Gn 0. And then the v little n is going to be equal to the maximum of gn and the expectation. Okay? That's like a weighted average, okay? Expectation. So considering an n-period binomial asset pricing model with the arbitrage condition, for each of the n's, let gn be a random variable depending on the first n coin tosses. Then we will have these two formulas here. So that's just the amount of stocks we have to hold and the Cn value. It's like a cash amount. We have that Cn is greater than or equal to 0 for all n. And if we set x0 equal to v0, we can define recursively the wealth equation. We also have xn is equal to vn for all n. In particular, xn is going to be greater than or equal to gm. Theorem shows that the American derivative security price given by the definition in this subsection is acceptable to the seller because they can construct a hedge for the short position. We next argue that it's also acceptable to the buyer. Let us fix n. Imagine that we've gotten to time n without the derivative security being exercised, and denote by tau star the stopping time that attains a maximum value in the definition. So this thing will hold true.
Why is
It's like it's, where was it? Because the seller will make more money for it. It's like it's kind of like this. Like, if you can prove these two conditions, if both of these conditions hold, what happens? A is greater than or equal to B. What happens? If these two things are equal, what happens? Sorry, if these two things are true, what happens? Yeah, so that's what it's saying there. It's saying like it's like one of them is like good enough for the buyer, and the other one is good enough for the seller, and they shake hands. Yeah. I know the maths is a bit complicated to look at, but that's what it's trying to say. Yeah, the maths is a bit cooked, but conceptually, it's okay. Where was I? Yeah. So there's that thing there. We're also going to have ck is equal to the indicator function when tau star is equal to k of gk. The owner of the derivative security exercises it according to stopping time, and she'll receive the cash flows at times n plus 1 and so on and so forth. At most, one of these ck values is non-zero, and if the option price is exercised at or before the expiration time n, then the ck corresponding to the exercise time is only non-zero payment. It's the only non-zero payment among them. However, on different paths, this payment might become different at different times. In any case, Vn will be equal to this thing there, and then this is going to become Vn equals this big expectation. Okay, so we can substitute for Cn, for Ck, sorry. For Ck is going to be the Gk times the indicator function. Yeah, these two things multiply to this. We saw in the theorem in chapter 2, which you haven't seen here. These are just the values of time n that the cash flows received respectively once the option holder decides to exercise this strategy. This is the exact contract that they hold, and thus to the American derivative security, Vn is acceptable to her. It remains to provide a method for the American derivative security owner to choose an optimal exercise time. We'll consider the problem with n equals 0, so that this achieves a maximum. So the stopping time tau is a minimum, maximizes the right-hand side, so it'll maximize this. The value of an American derivative security is always greater than or equal to the intrinsic value. Stop time tau is the first time that these two are equal. For example, the value of an American put is always going to be greater than or equal to 0, but the put can always be out of the money. So in this case, the minimum in the formula above is over the empty set, and we follow the mathematical convention of the minimum over the empty set being infinity. Okay. American call options. Okay, let's speed through this. So we saw in slide 17, it becomes optimal to exercise an American put value. For an American call on a non-dividend paying stock, there's no advantage to early exercise. Okay, so for put options, it's good. For call options, it's not good. This is a consequence of Jensen's inequality for conditional expectations. It's not better to exercise early. Yeah, weird result. Oh, so it's like, what's Jensen's inequality? The E is bigger. So like you have a convex function G. So due to this thing, basically, G is a convex function, then this will hold. So if G, so as we say here, if G is a convex function, this thing here will hold. For instance, we might have G of S is S minus K, the maximum payoff of a core strike, of a core with strike K. So here's a convex function. Yeah, basically it's like, how do you see the intuition here? It's like a, not sure you can see it from there, but yeah, well, let's see this one. So considering an n-period binomial model, in this model, consider an American derivative security with convex payoff function. The value of this derivative security is going to be this thing here, this big thing, and then for European derivative security, it's going to be this. So it's slightly different. For the American, the max is out the front. For this one, the max is inside. This theorem shows that the early exercise feature of the American core contributes nothing because it's a discounted intrinsic value of the core and it's a sub-martingale. So, yeah. Then discounted intrinsic value in American put is not a sub-martingale. Jensen's inequality says that the convex payoff of the put imparts the discounted intrinsic value of the put, a tendency to rise over time, but this may be overcome by a second effect. Because the owner of the put receives K upon exercise, she may exercise early in order to prevent the value of this payment from being discounted away. For low stock prices, this second effect becomes more important than the convexity, and early exercise becomes optimal. For the call, the owner pays K and prefers that the value of this payment be discounted away before exercise. This reinforces the convexity effect and makes early exercise undesirable. And then we have a summary here, which I won't go over because we're out of time. But thank you for coming. And also the references is chapter 4 of Shreve's book before we get a copyright strike.